Today I wanted to talk about the idea of protein folding and unfolding, and how can one uh, 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 measure the stability of a protein and understand the details of protein folding and folding problem, which is sorted by now. So I have uh, a plan to uh, uh, make establish a discussion on it based on a paper from Professor Jayant Udgonkar's lab. So this paper uh, is a folding and folding study of SS3 domain of PI3 kinase. So it is a 10 kilodalton protein, and so using urea and guanidinium hydrochloride, the protein was folded and folded, and its uh, uh, equilibrium and kinetic study was performed using fluorescence and circular diachorism data. So let's read the abstract first. So it says that kinetic and equilibrium studies of protein folding and unfolding of the SS3 domain of PI3 kinase have been used to identify a folding intermediate that forms after rate limiting step on folding pathway. So folding and unfolding in urea as well as in guanidinium hydrochloride were studied by monitored changes in intrinsic fluorescence or in the far UV circular diachorism of the protein. Now, uh, basically these chaotrops like urea and guanidinium hydrochloride, they stabilize the unfolded conformation, and the equilibrium that exists between native and unfolded conformation, it shifts the equilibrium towards unfolded conformation, and more protein gets unfolded. And how can one study this phenomena? So they look for something that is different in folded versus unfolded. So that can be fluorescence. Fluorescence, whenever protein conformation changes, its fluorescence changes because the fluorescence property of the fluorophore depends on the microenvironment around it. And let's say protein, if the fluorophore, maybe it's intrinsic fluorophore, tyrosine, tryptophan, or some other dye also which gets labeled to protein to study its behavior. If it is in its hydrophobic environment, then it will show different fluorescence property. And if it is exposed to hydrophilic environment, then it will show different fluorescence property. And one who basically whenever you study the change of any protein in terms of its conformation or any reaction, then you generally look for property that can distinguish the reactant and product. And here product is, let's say, unfolded conformation, and reactant is native conformation. And the native conformation has distinguished fluorescence property, absorbance property, CD spectroscopy property, and based on this property one can distinguish and study the kinetics of the protein. So same has been done with this protein, and it is saying that the two probes yield non-coincident equilibrium transition of unfolding in urea, indicating that an intermediate I exists in equilibrium with native and unfolded protein during unfolding. Uh, so we'll see for it that what it is, that the the equilibrium unfolding curve monitored by fluorescence and equilibrium unfolding curve monitored by circular diachorism, they don't coincident on each other, they don't fall on each other. And most likely because when you monitor far UV circular diachorism, it's essentially indicate about secondary structure of the protein. And when you study fluorescence, that is indeed a measure of sort of tertiary structure of the protein. So let's suppose uh, during the unfolding, let's say tertiary structure is unfolded completely, but some secondary structure remained in the unfolded conformation, or even during at a urea concentration which is in the midway. So what will happen? You will have a structure conformation that is stabilized at that particular uh, urea concentration, because no, so basically when you monitor it by fluorescence, then you will look for how tertiary structure is changing, and when you look by circular dichroism, then you look for how secondary structure is changing, and if they are changing differently, that means okay, so some conformation exists. So we'll discuss about it. So an intermediate is observed also in the kinetic unfolding studies, and in the presence and its presence lead to the unfolding reaction in urea as well as in guanidinium hydrochloride occurring in two steps. Now the unfolding reaction in urea as well as in guanidinium hydrochloride occurring in two steps. The fast step is completely within initial 11 milliseconds of unfolding and manifests itself in a burst phase change in fluorescence. At high concentration of guanidinium hydrochloride, the entire change in fluorescence during unfolding occurs during the 11 millisecond burst phase. CD measurements indicate, however, that I retains an like secondary structure. An analysis of kinetic and thermodynamic data according to a minimal three-state N to I to U mechanism, position I after a rate-limiting transition state Ts1 of folding on the reaction coordinate of folding in guanidinium hydrochloride. Hence, I is not revealed when folding is commenced from U, regardless of the nature of probes used to follow the folding reaction. Interrupted unfolding experiment in which the protein is unfolded transiently in guanidinium hydrochloride for various lengths of time before being refolded showed that I refolds to N much faster than U. Confirms the analysis of the direct folding and unfolding experiments that I is formed after the rate limiting steps of refolding in guanidinium hydrochloride. Now let's look what has been the argument that this paper presents. So basically, two experiments have been performed. This is the equilibrium unfolding experiment. One is monitored by CD, another is by fluorescence. This is the apparent F. So, so this is the whole paper, and we will start discussing it. So there has been considerable controversy about the role of folding intermediate in protein folding because of the discovery that many proteins fold in an apparently two-state U to N manner from the unfolded state to the native state. The controversy has abated now with the realization that number one, the kinetic criteria used to define a protein as two-state folder are obviously to high energy intermediates that may be populated transiently and marginally either before or after the rate limiting steps. Second, such scarcely populated intermediates can now be detected by the application of high resolution probes like NMR to study the folding of apparent two state folders. Third, for proteins that appear to fold or unfold by two state mechanism in one state of condition, in one set of conditions, intermediates can be induced to accumulate in another set of condition or upon mutation. 4. The deviation from linearity in the dependence of denaturant concentration of the activation free energy of folding or unfolding, or both, have been observed for a number of apparent two-state folders and ascribed to sequential folding mechanism with one or more intermediates between U and N. It seems clear now that for many of the apparent two-state folders, it is merely a question of using the right folding condition or of using the right experimental probe before a folding intermediate is revealed. Revealing an otherwise concealed intermediate is important because folding intermediates serve as signposts on folding pathways. In absence of such signpost, it is difficult to define a folding pathway and to distinguish one pathway from alternative pathway that may be used in different folding conditions. The structural characterization of late folding intermediate will allow the most direct determination of the sequence of events that occur late on the folding pathway. To identify and characterize folding intermediates, there are concealed uh, after the rate limiting steps has been a difficult challenge. The possibility of such intermediates was first suggested by native state hydrogen exchange study that indicated that the native state exists in equilibrium with many different partially unfolded forms. In the case of ribonuclease A, it has been shown that one such partially unfolded form is an unfolding intermediate that accumulates on the direct unfolding pathways. Such intermediate, which precede the rate limiting step in unfolding, might be the same as the intermediates that are concealed after the rate limiting steps of folding. Thus, one approach to detect intermediates that populate after the rate limiting steps of folding is to detect partially unfolded intermediates in kinetic unfolding studies. Now, partially unfolded intermediates have been detected in kinetic studies of unfolding of several proteins. It is important to characterize such intermediates because partially unfolded forms very often aggregate to form amyloid, protofibril, and fibrils. Now, a major group of two-state folding protein is that of SS3 domain, which are found in signal transduction and cytoskeletal proteins, where they provide the interaction surface for the assembly of multimeric protein-protein complex. SS3 domains are composed of 60 to 85 amino acids residues, and they all have a similar 3D fold called the beta barrel fold. Now, SS3 domain forms many different proteins that have been used as a model system to address various important aspects of protein folding, such as the nature of protein folding transition state and the relationship between protein topology and folding pathway. The folding of SS3 domains has been studied by protein engineering methods, NMR, as well as by computational studies. Recently, the characterization of very scarcely populated folding intermediate preceding the rate limiting step during the folding of Finn and Ebb SS3 domains became possible within the advent of new NMR methods. So, no unfolding intermediate has been reported for any of the SS3 domains, but partially unfolded conformation of many different SS3 domains have been observed under native condition when their dynamics were studied by hydrogen deuterium exchange in conjunction with mass spectroscopy. So SS3 domain of PI3 kinase consists of 83 residue threaded through 5 beta strands and 2 helix-like turns. The 5 beta strands are arranged in 2 beta sheets that are orthogonal to each other. The folding of SS3 domain of PI3 kinase was studied earlier using various optical probes and real-time 1D NMR. It appeared that SS3 domain of PI3 kinase refolds and unfolds by a two-state mechanism based on comparison of the values of free energy and of unfolding and its dependence on denaturant conditions, uh, denaturant concentration obtained from kinetic and equilibrium studies. So here we have studied the folding and unfolding of SS3 domain of the PI3 kinase in urea as well as in guanidinium hydrochloride by monitoring the change in intrinsic fluorescence. Now, an equilibrium unfolding intermediate I is shown to be populated during urea-induced unfolding. A burst phase change in fluorescence whose amplitude increases with an increase in denaturant concentration is observed during the unfolding of protein in urea as well as in guanidinium hydrochloride. Now, the product of burst phase is shown to be a partially unfolded intermediate which express less surface area to solvent than does U and which refolds to N much faster than does U. So, all the thermodynamic and kinetic data can be described adequately on the basis of simple minimal 3-state N to I to U mechanism, suggesting that the same intermediate I is seen in the equilibrium and kinetic studies. The analysis indicates that I forms after the rate limiting step during the folding of this SS3 domain in guanidinium hydrochloride. Now, the first result is equilibrium unfolding. So, we will refer to figure number 1 shows the equilibrium unfolding transition of SS3 domain. So, since now we are at an important point. So, equilibrium unfolding transition of SS3 domain with both urea and guanidinium hydrochlorides as denaturants. So, in the case of urea induced unfolding, it is saying that fluorescence monitored and far UV CD monitor unfolding transitions are not coincide. Okay, so indicating that an equilibrium unfolding intermediate is populated during unfolding of N and U. So this is mainly about in the case of urea induced unfolding. So yeah, of course, in the equilibrium unfolding experiment. Now, in the case of guanidinium hydrochloride induced unfolding, the far UV-CD monitor unfold transition has an anomalous shape, but it has appeared not to be coincident with the fluorescence monitor transition. Hence, both the urea and guanidinium hydrochloride unfolding needs to be analyzed on the basis of three-state mechanism according to equation 4. So, since the loss of fluorescence is seen to precede the loss of far UV-CD during unfolding, the simplest assumptions to make in the analysis is that fluorescence properties of I are same as of U. So, this first thing that the author is saying that uh, that since it says that since the loss of fluorescence in C happens first before then losing the secondary structure, so it essentially indicates that fluorescence properties of I is same as of U, and that the far UV-CD property I is same as the N. So why? Because far UV-CD structure is happening uh, uh, first, right? Yeah, I mean it happens late. So where I forms, so I ka CD like property is similar to N, and fluorescence like property of I is like U. So that's why as soon as I forms in the solution, the native state fluorescence shifts to unfolded like conformation, and that's why in the melt uh, it will fall down uh, before far UV-CD spectra falls, because the same eye has the CD property similar to N like. So even if I forms, the CD spectra property will not change such that I will look like such that I will contribute to N fluorescence N CD spectra, not to U series CD intensity means I'm talking about. So, so these assumptions amount to treating the fluorescence monitored equilibrium unfolding curve as one monitoring the loss in tertiary structure, yeah, as it is evident, and the far UV-CD spectra is uh, as a monitoring loss of secondary structure. Okay, so but nevertheless, even with these assumptions, it is difficult to extract reliably the values of all four thermodynamic parameters, which are um, delta G N to I, delta G I to U, M value N to I, and M value I to U. So there will be four parameter, of course, if to transition. So from the three state analysis of the equilibrium urea induced unfolding transition, and especially for the guanidinium hydrochloride induced unfolding transition. Now, refolding and unfolding kinetics. Unfolded protein in 4 molar guanidinium hydrochloride or in 6 molar urea was refolded by diluting the denaturant to different concentration below the midpoint of the equilibrium. Okay, so unfolding protein in 4 molar guanidinium hydrochloride or in 6 molar urea was, I'm talking about now next the kinetic experiment, uh, was refolded by diluting the denaturant to different concentration below the midpoint of equilibrium unfolding, midpoint means Cm, and the kinetics were monitored by change in fluorescence at 300 nanometer. So, uh, uh, figure 2a and b, so this is the A and B, show representative kinetic refolding traces in different concentration of urea and guanidinium hydrochloride respectively. Now, a major refolding phase and a slower phase corresponding to propyl peptide bond isomerization was observed when refolding was carried out in the urea concentration lower than 1.5 molar. Okay. So, let us see that in 2A and B. Uh, so, A and B are essentially, one can read here, a representative kinetic refold when unfolded protein in 6 molar urea was refolded to 2.96, 2.5, 2 molar and 0.8 molar top to bottom. The refolding trace for 0.8 molar urea was fit to a double exponential equation, while refolding trace for 2 molar urea fit to a single exponential equation. So, this is also to be noted here. Now, the signal of unfolded protein, so here it is here. So, this would be jump from 6 molar urea to 2.96, second is 2.5 molar, third is 2 molar, and this is 0.8 molar, and this is fit to the double exponential. However, 2.96, 2.5 and 2 is fitted to a single exponential equation. Now, the signal of unfolded protein in 6 molar urea to which the kinetic curves were normalized is shown as broken line. So, this is the signal of unfolded protein in 6 molar urea. So, this fluorescence loss is called the burst phase. Now, what is B? This is also important. Now, B is in the guanidinium hydrochloride. So, we will take B as purple. So, representative kinetic traces of refolding in this is 1.1 molar, 1 molar, 0.8 molar and 0.53 molar top to bottom. The kinetic traces were normalized to the value of one of the unfolded protein in 4 molar guanidinium hydrochloride as shown as the broken line, this one. So, the continuous lines show the fits to a single exponential equation for the 1.1, 1. Molar and to a double exponential equation. So, if as you see that when concentration is uh, uh, low or concentration of donation, then there is a one more exponential equation that is evident, is been discussed here, that the kinetics in urea concentration greater than 1.5 ml 5 molar are signal exponential because of refolding rates appear to become comparable to the rate of prolyl peptide bond isomerization. Now, in the case of guanidinium hydrochloride, also prolyl isomerization phase was observed in addition to a major refolding phase when unfolding was carried out to a final concentration of 0.9 molar and a single exponential. Okay, so the sorry here. So, a major refolding phase and a slower phase corresponding to a prolyl peptide bond. So, slower phase is for prolyl peptide bond isomerization. Okay. prolyl peptide bond isomerization was observed when refolding was carried out in a final U concentration of urea lower than 1.5 molar. So here you see uh, in this thing that 0.8 molar fitted to double exponential. Rest is, and here also it is also double exponential 1.8 molar or 0.53 guanidinium hydrochloride. Now same is means that the kinetics in urea concentration greater than 1.5 molar are single exponential. The same thing because the refolding rates appear to become comparable to rate of prolyl peptide bond isomerization. So if one can look for it, then they'll get to understand. So in the case of guanidinium hydrochloride also, a prolyl peptide bond isomerization phase was observed in addition to the major refolding phase when refolding was carried out in final concentration of guanidinium hydrochloride below 0.9 molar, and a single refolding phase was observed in final concentration uh, above 0.9 molar. Yes, that's true. Okay. Now, figure 2C, this one, and D represent fluorescence monitor unfolding traces. So this both were CD. No, so A and B as fluorescence monitor, and C and D representative fluorescence monitor unfolding traces in different concentration of guanidinium hydrochloride respectively. In both denaturants, the kinetic traces do not extrapolate to protein signal at T is equal to 0. Uh, in both denaturants, okay, yes. So in both denaturants, the kinetic traces do not extrapolate to native protein signal but to values higher than the native protein signal depending upon the denaturant concentration. So hence there appears to be a burst phase change in fluorescence during the dead time of stop flow mixer, since the subsequent observable phase is relatively slow. Since the subsequent observable phase is relatively slow, occurring in 100-second time domain, the initial burst phase cannot be experimental artifact of the sort that could conceivably arise in instances where the subsequent observable kinetic phase is very fast. Now the observed phase is well described as a single exponential equations. No unfolding trace was observed at concentration of guanidinium hydrochloride greater than 3.5 molar, indicating that the entire fluorescence change during unfolding takes place during 11 milliseconds of the burst phase. It should be noted that the observation of a denaturant dependent burst phase change in fluorescence during, and this point is important, like so the entire fluorescence change during unfolding takes place when concentration is around greater than 3.5 molar guanidinium hydrochloride, then this happens. So it should be noted that the observation of a denaturant dependent burst phase change in fluorescence during stop flow measurement of unfolding seen here for SS3 domain is unusual and has not been able to uh, has not for example been seen in similar recent studies of denaturant induced unfolding of several other proteins. Now to confirm that the observed burst phase change in fluorescence observed in stop flow measurements was not an artifact, manual mixing experiments were done in all concentration of guanidinium hydrochloride and urea in which the observable unfolding rates could be measured precisely. When the observed unfolding rates were slower than uh, 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 0.27 second inverse and hence amenable to measurement by manual mixing experiments with a dead time of 10 seconds. Now the single exponential fits to the kinetic unfolding traces should be extrapolated reliably to t is equal to 0 for determination of the burst phase change in fluorescence. The inset in figure 2c, if you see here, in figure 2c, so this one, and D show the burst phase changes in fluorescence is seen in stopped flow mixing experiments and the manual mixing experiments. So the burst phase change in fluorescence is seen in stopped flow mixing experiments and in the manual mixing experiments. What? The insets show the burst phase change in fluorescence is seen in so it shows the, so here the C and D, if I can quickly change the color. Okay, so C is representative traces of unfolding in 8 molar urea, 7 molar urea and 6 molar urea, right, top to bottom. From stopped flow experiments, all the traces were fitted to single exponential equation and normalized with respect to the t is equal to infinity point of the unfolding traces in 6 molar of urea. Now the native protein signal is shown in broken line. This is the burst phase, a very big burst phase. Uh, okay, now the so the inset in C shows representative traces of unfolding in 8 molar, 7 molar, 6 molar urea from manual mixing experiment. So here also there is a big uh, uh, the burst phase. Now the D, the representative traces of unfolding in 3 molar, 2.5 molar, 2.2 molar guanidinium hydrochloride top to bottom. The continuous line show the data represents fits to a single exponential equation, and broken lines show native protein signal. Here also the fluorescence signal of protein in 4 molar guanidinium hydrochloride was taken as 1. Here also the fluorescence signal of the protein in 4 molar guanidinium hydrochloride was taken as 1. The inside D show representative traces in the manual mixing experiments. So now coming to the insets in figure 2C and D show the burst phase changes in fluorescence is seen in stopped flow experiments as well as in the manual mixing experiments. Now the relative amplitude of the burst phase fluorescence change as well as the apparent rate constant of the observed kinetic phase was the same for manual mixing and stopped flow mixing experiment at the same concentration of denaturant. Now figure 3A and B, 3A and B, yeah, 3A and B. Figure 3A and B compare the kinetic and equilibrium amplitude. Now, figure 3A and B compare the kinetic and equilibrium amplitude of fluorescence monitored folding and unfolding in urea as well as in the guanidinium hydrochloride. Compare the kinetic and equilibrium amplitudes of fluorescence monitored folding and unfolding in urea as well as in guanidinium hydrochloride. So let's see what this figure is. So in figure A, I can think of that this is the melt acquired at uh, 300 nanometer. Let's see here the comparison of equilibrium and kinetic amplitudes. So this is okay uh, uh, by monitored by a change in fluorescence at 300 nanometer A and B. Both are 300 nanometer A and B, right? Now so as well as by a change in ellipticity. Okay, so as well as by a change in ellipticity, and that thing is, let me draw it in blue. So uh, A and B is the by fluorescence at 300 and by change in ellipticity is C. Okay, this one are compared when urea A and C are urea and B is guanidinium hydrochloride were used as denaturant. Okay, now O equilibrium unfolding. Okay, so the circle the circle the circle is the circle is the open circle is equilibrium unfolding experiment. See here, these open circles are equilibrium unfolding experiments, and uh, these circles, these triangles, the filled triangles, the black filled triangles. So so they are so they are so they are signal at t is equal to infinity. Okay, so as so at every urea concentration they have the signal. When completely things are fine in the kinetic experiment, the signal that we get after the end, so it should be falling on this thing only. It should be the same, completely equilibrated, right? So the signal that we get from the kinetic experiment should be on the top of equilibrium experiments. So that what is sort of evident here. Now the open triangle R T is equal to 0 points of the kinetic unfolding traces, and that also makes sense that as soon as you uh, uh, mix two things and take the measurements after mixing, so what will be the signal? That signal will should be you know should be the mm, should be on the baseline, like the this is the unfolded baseline at t is equal to 0, and this is the uh, native baseline, so it's something like here, but this is also so the okay so now there are some circles facing down, like ulta triangle and ulta triangle open are t infinity and t is equal to 0 points. Okay, so I don't know, so these are Siddha triangles, so these are t is equal to 0 points of kinetic refolding traces. So when protein is getting refolded in just t is equal to 0, all the protein will remain in unfolded uh, conformation. So that's why they should fall in on the unfolded baseline, and uh, some should so and in the I need to change the color. So see uh, yeah, so see that triangle is t is equal to 0 points of the kinetic refolding traces, means at t is equal to 0 all the protein remains unfolded, and and uh, so again here for the unfolding experiment, for the unfolding experiment, ulta circle, ulta triangle, both filled and unfilled, both are uh, for the unfolding experiments, means at t is equal to 0, at t is equal to 0 they will be at t is equal to 0 they will be at in its native conformation, so it should fall on native baseline. Okay, so what is this baseline? Why does the signal changes at different concentration if the protein remains in its native conformation? Is this is the effect of urea, means if there are urea in around the protein, so the fluorescence value will change as per the urea concentration in it. So now the kinetic data were normalized to unfolding data by using either the signal of unfolded protein in 6 molar of urea. Now one thing we missed, that uh, for A to C, so for all the traces, so the Seedha triangle, the Seedha filled triangle, so this one, this one, this one, this one, this one, till here. Okay, so these are for the refolding traces, means T infinity after refolding. So T infinity after refolding, so it should have fluorescence signal similar to the native conformation. Okay, and rest apart from this all are ulta filled triangle, and so these all ulta filled triangle, they all are having um, they all are having fluorescence value, they all are having fluorescence, they are all are for the unfolding experiments. So in at t is equal to infinity, all these are unfolded, completely unfolded, means not completely unfolded, some will be in this conformation, some will be in this conformation, in native conformation, and so everything means that will be the finally, you know, so just one rule, ulta triangles are the result of unfolding traces, means uh, protein will remain in unfolded conformation, and final signal at t is equal to infinity, protein will remain in unfolded conformation at that, so equilibrated, and it will show like this, and this is for the refolding, means protein will remain in the, so that's why they are falling in the native baseline only, and yes. Now, kinetic data were normalized to equilibrium data by using either the signal of the unfolded protein in 6 molar urea A or in 4 molar guanidinium hydrochloride B. So, the difference here and here is only it's guanidinium hydrochloride and it's urea. So, okay. So, or the signal of unfolded protein 7.5 molar urea C. Okay. So, here they have used more urea. Now, the continuous lines through the urea-induced equilibrium unfolding data in A and C are drawn according to equation 1 using the values of delta GNI, delta GNU, MNI and uh, MNU given in the legend to figure 1. Now, where is the equation 1? We need to see the equation 1. Okay, so here's the equation 1. So equation 1 is the far UV-CD and fluorescence monitor equilibrium unfolding transition were analyzed together using a 3-state model, and for such unfolding mechanism the observed optical signal is given by Y observed is equal to Yn plus Yn plus Yu minus Yn Zi e to the power minus delta G Ni by RT plus Yu e to the power minus delta G Nu by RT divided by E plus e to the power minus delta G Ni by RT plus E to the power minus delta G Nu by RT, where Yn and Yu are optical signals of the native and unfolded proteins. So Yn and Yu are optical signals of the native and unfolded proteins respectively. Now delta GNI and delta GNU is equal to delta GNI plus delta GIU are the free energy of unfolding of N to U and to U respectively, and delta GIU is the free energy of unfolding of I to U. Now Zi is a measure of optical signal of I, Yi relative to Yn and Yu, and is given by Zi equal to Ui minus Un by Yu minus Yn. So it is the third equation. So basically this is the fit, and using this fit they could get all these parameters. They have taken Z I as 1 for the data in A and 0 for the data in C. So we'll see for it why it is different. Now the continuous line through the T is equal to 0 points of the kinetic unfolding traces are fixed to equation 8. Now kinetic traces are fixed to equation number 8. So this is the equation. So the curve traced by the T is equal to 0 points of the kinetic unfolding traces were fit to a two-state n to I model by y observed is equal to yn plus yi e to the power minus delta g ni by rt divided by 1 plus e to the power minus delta g ni by rt. Now the continuous line through T is equal to 0 points of the kinetic unfolding traces are fixed to equation number 8 and yielded values for delta G and I uh, uh, and Mi of 2.1 kilocalorie per mole and minus 4.8 kilocalorie per mole respectively for the urea data in A and 3.7 kilocalorie mole respectively.